Welcome back. Okay, so now we're going to talk about conductivity and how to induce charges in an object. Okay, so objects can be broken up into two basic groups, conductors and insulators. So for conductors, they're usually metal and they have loosely bound electrons, so charge flows freely. Insulators have tightly bound electrons, so it means that the electrons cannot move as easily on the surface of the object. Okay, so induction in a conductor. Okay, so, well, this is our little microphone. So let's pretend this is just a ball right here, a metal ball, and it's neutral because we have the same amount of protons and neutrons on here. And everything is pretty much evenly spaced throughout this metal ball. Then we bring a charged object, so let's pretend this is the ebonite, close to this ball. Now we'll show you in class how to charge objects, and we'll do that together. We could tell from the picture here that this ebonite is negatively charged because it has much more negative charges on here than the positive charges as indicated. Okay, so when we bring this ebonite closer to this metal ball, how will the positive charges move? Think about it and answer. That's right. You should have said that positive charges don't move at all because the positive charges are connected to the lattice of the structure. They're part of the atom. You can move electrons, but you can't move positive charges. If you can move positive charges, you can imagine it would be like this free-flowing, looks like the Terminator thing, that this metal would just morph and move because the lattice of the structure would be moving at that point. So positive charges don't leave or come into an object. They also don't move. They're stationary. It's the electrons that move. So negative charges, well, opposites attract, likes repel. So the negative charges on this metal ball, this conductor, will be repelled by the ebonite. So would it look like this? There's a problem. Do you guys see it? So let's go back to the original. So we bring it in. It's going to look more like this. It's not that the ebonite's going to strip all the electrons from one side and push them all the way to the other side. It's that some of the electrons will shift to the other side. So if you look on one side of the ball, it will look like it's positively charged. And if you look at the other side of the ball, it'll look like it's negatively charged. So if we look at the forces on this ball, this positive side is attracted to the negative ebonite, and this negative side is repelled by the ebonite. But since this negative side is further away, it actually has a weaker force because the further away we get, it's not as strong. So even though that this metal conductor is still neutral, there's still the equal number of positive and negatives. So if you count all the positives, you count all the negatives, they still even each other out. But because you have positives on one side and negatives on the other, and the negative side is further away from your ebonite over here, you're going to have a smaller force. So you'll have a net force of this neutral conductor being pulled to your ebonite. Pretty cool, huh? Now let's see what would happen if we use glass. Glass is not a conductor, it's an insulator. So you could think of it as the positives and negative charges are bound together, but they can shift around. So we bring our same ebonite closer to the glass, and let's see what happens. A couple of these little eggy shapes with the positives and negatives get closer, they shift around. So if we look just at the surface of the glass, it looks like it's positively charged. So this ebonite will have a net force towards the glass. It won't be as strong as the conductor, but it is still there and still present. Okay, so conductors charge flows and insulators charge shifts. And that's the thing to remember. Okay.